Hello, welcome to today's lesson. We're going to continue our work today with angle sum and difference formulas. By the way, these are sometimes called angle sum and difference identities. So these are formulas, they're also identities. First thing, yesterday in one of the times you saw the tangent formula, I accidentally only wrote tangent B down here. So double check your notes from yesterday, please. The tangent sum and difference formula should be this, with the denominator being 1 minus plus tan U times tan B. So thank you for pointing that out to me. Please don't hesitate to let me know if I make a mistake, especially something important like that. I do make mistakes, and it helps me if you let me know. So thanks. Before we get back into doing problems, because what we're going to do today is we're going to solve some equations with these and verify some identities with these. You'll get a little more practice evaluating today as well. But evaluating we did yesterday, and I'm going to introduce these two types of problems today. But before we do that, I just wanted to share with you, when we started this section, we talked about some things in math that work the way you expect them to, and some things in math that don't work the way you expect them to. The most common answer for things that don't work the way you expect was really this one. I saw this a lot. And I just wanted to share with you, these were the ones that I wrote down. I wanted to share with you some that your classmates came up with. So here are some of those things in math that work the way you want, and then things that didn't. So splitting apart a fraction when the denominator has one term, yeah, go for it. But if the denominator has two terms, you would think that you could do this, but that doesn't work. So even though these kind of look similar, this one does work intuitively the way you want it to. And this one, absolutely not. A lot of people, for things work the way they expect them to, said tan and cotan being reciprocals. Somebody said that a 45, 45, 90 made by cutting a square along the diagonal. Sequences and series. A few people mentioned sequences and series. They just seem to make sense to you when you learn them. Even functions, a couple people mentioned. I thought this one was interesting, this pairing, taking you way back to elementary school. So positive times a positive being a positive, that totally made sense. But picture yourself back in elementary school when the first time you heard a negative times a negative was a positive. I'm sure that didn't make sense. All right, but now we all go along with it because we know that that's true. Other things you mentioned for things that didn't work the way you wanted to, that the 3 goes with the 6 for pi over 3 and 60. This one I forgot. I always love this example, that when you rotate clockwise, it's negative, counterclockwise is positive. The first time we did that, it didn't make sense. But then when we realized that from the initial side going up would be positive, then it did make sense that counterclockwise was positive. And a few people also mentioned, for things that didn't work the way you expected, graphing inverses, which I thought was kind of interesting. A number of people mentioned that one. And logs, pretty much everything about logs doesn't make sense the first time you see it. But hopefully now that we've learned it, it's better. We'll be reviewing that when we get up to the review lessons. Okay, so let's check out a couple problems. And the first one we're going to do together is a verify algebraically. So this side is equal to this side. The question mark's there just to remind you that you can't divide both sides by 2. You can't add this to the other side. So our job for verify algebraically is to prove that this side equals this side. So we want to show that the two sides are equal. When you first look at this, you might have a lot of ideas. A lot of times students want to try to combine these, but you can't because the angles don't match. The angle here is x plus pi. The angle here is pi minus x. Sometimes when people see these, they want to try to make this tan x plus tan pi, but you definitely can't do that because in this section 5.4, we've learned that you can't just, if you have a trig function and a sum or difference inside, you can't just do the trig function of the first term and the trig function of the second term. It doesn't work like that. So here's what we're going to do instead. You want to train yourself. Whenever you see a trig function, whether it's sine, cosine, tangent, any trig function, if you see a sum inside, you want to think of these sum and difference formulas. When you see a trig function, you see a difference inside, you want to think of the formulas for the sum and difference. Okay? So anytime you see a sum or a difference inside of a trig function, you want to apply those formulas. So let's apply the tangent formula here. I'm just making like a little brackety thing there because this is going to end up being a pretty big fraction. So it's tangent of the first angle plus tangent of the second angle. And then the denominator is 1 minus tangent first angle, tangent second angle. And that's just that first expression. So that's why I put the little bracket thing there. Because if I didn't put that, a lot of times this is so big that people think it's the entire expression expanded. But it's really just this piece so far. We still have to do this piece. So it's going to be tangent of the first angle minus tangent of the second angle over 1 plus, because for the tangent formula, you keep the sign up top, use the opposite sign on the bottom. And then we need the product of both those tangents. This was so big, I didn't even leave enough room. Okay. So that's this one. All right. Now we need to continue and see what our next step will be. This looks like a mess. I would say it even looks worse than what we started with, but it's actually quite nice once you know the next step. So to help you with the next step, I'll ask you a question. How many variables are there on this side right now? The answer to that is 1. The only variable in that entire expression is x, because pi is not a variable. Pi is a number, and in particular, it's an angle. So if we think of pi or sketch pi, we can find the tangent of pi. The point on the terminal side is -1, 0. And since tangent's definition is y over x, we get 0 over -1. And the tangent of pi is 0. So what that means is, on the left-hand side here, anywhere we see the tangent of pi, we can replace it with 0. So in this fraction, the tangent of pi becomes 0 in the numerator. In the denominator, the tangent of pi becomes 0. And as you can see, this is going to clean up pretty nicely, because when you multiply by 0, it becomes 0, and 1 minus 0 is just going to be 1. But I want to show all the steps, because we already know the answer. We're going to end up with this. Our job is to show that we really get there. And then in the next fraction, we have 0 minus tan x plus over 1 plus 0 times tan x. So this fraction becomes tan x over 1, because 1 minus 0 is 1. So that's just going to be tangent. This fraction, the numerator becomes negative tangent. The denominator becomes 1 plus 0. And when you have minus and negative, you end up with plus, and tangent plus tangent is 2 tangent x. So what happened here is I had minus and negative, and that becomes plus, and I got 2 tangent x. So I love this problem because I think it's really surprising. When you start it and you expand both of these tangents, it looks so much worse than what you started with. But the key to this problem, and the key to a lot of other problems, is remembering that pi is an angle. It's not a variable. The only variable here is x. So that's going to be a key to this problem and many others. Let's continue on to number 2. Number 2 is a solving equation kind of problem. And we're going to find the solutions in 0 to 2 pi. So when we go to solve, we're looking for a particular value of x. We'll know we're finished when we have x equals. Okay, so we're looking for the x that you could plug in here and here that makes the two sides equal. And I mention that because it's very different than verify. When you verify, you're trying to show this side equals this side. You're trying to show they're always the same. When you're solving in an equation, you're looking for a particular value of x or particular values of x that satisfy this equation. So keep that in mind. Okay, so we cannot combine these because the angles don't match. X plus pi over 3 is different than x minus pi over 3. But what we can do is train ourselves that anytime we see a trig function with a sum inside, we can expand. And anytime we see a trig function with a difference inside, we can expand. And that's what we're going to do. So using our formulas, you can look back at them because I know they're still new to you. The sine angle sum formula is sine of the first angle, cosine of the second angle, plus I like to do sine second angle, cosine first angle to keep it sine cos, sine cos. Those of you who prefer keeping the angles in the same order, x pi over 3, you could make this cos x sine pi over 3. You could switch the order of those two for sure. Okay, and you don't have to put the brackety things, but I like to put them to remind me that this one term became 2. And then I'm going to bring down this plus, and then we have to expand this one. So it's sine x cosine pi over 3. And then the way I prefer the formula is minus sine pi over 3 cosine x. And that's the expansion of the left-hand side, and that's equal to 1. So the next step we want to take is to look at the terms. We have 4 terms. 1, 2, 3, 4. With these types of equations, what should happen every time is 2 of the terms should cancel. See, I'll have a sine pi over 3 cosine x and a sine pi over 3 cosine x. Those should cancel, and the other 2 should combine. So this is a 1 sine x cosine pi over 3, and this is another 1 sine x cosine pi over 3. So altogether, I have 2 of those. And the reason that's going to kind of happen every time you do one of these is because we can't, like with these formulas, we can't magically solve every equation that exists now. But for equations of the structure of this format, we can now apply these formulas and solve. So this is an equation that a couple days ago we couldn't have solved, but with the new formulas you can. So that's why almost every time you're doing a solve problem in this section, you're going to get 2 terms that cancel and 2 terms that combine. Now, from here, we have different options. We can move the 2 over by dividing, or we can go ahead and evaluate cosine of pi over 3 now. And we actually could have evaluated cosine of pi over 3 back here, but I personally find it much easier to cancel and combine terms first. Cancel and combine terms first. So that's why I did that. And now what I like to do is I like to evaluate next. But you totally could move the 2 over next instead if you like. For the cosine of pi over 3, that's the cosine of 60. So you can use your triangle or your unit circle, and the cosine of 60 is 1/2. This 2 times 1/2 is going to become 1. They're basically going to reduce each other out. And if it's tough to see that, here's something that can help. Multiplication is commutative, so you could switch the order of the 1/2 and the sine x. And now you can clearly see that the 2 and 1/2 are going to reduce. And all we have left to do is solve for where sine equals 1. So to do that, our reference angle is not going to be 30, 60, or 45. None of those are going to work. It's going to be a quadrant angle. So we'll all be using the unit circle on this one. And since sine is the y-coordinate, we're looking at an answer of pi over 2. This particular equation only has one answer, but beware, you could have more answers. So just be aware of that. You don't always get exactly one answer for this type of problem. So just to recap the steps that we took, we expanded both of these sum and differences. We canceled and combined. We evaluated, because there's an angle in there. We simplified the equation, and then we solved the equation. One more thing to be aware of in this problem is this one has a plus right here. If you get a problem where this is a minus, you have to be careful. So picture this being a minus here. You would have to be careful because this one term became 2. So if this were a minus here, you would have to distribute it. So you would be required to use parentheses or brackets or go ahead and distribute. And you'll get a practice problem on that soon enough. So I'll let you practice that when we get to it. All right, so that's a solve problem. What you're going to do next is you're going to do some practice problems on your own. And sometimes I just send you into Google Classroom and give you an answer key. But I find these problems can be more difficult and tricky. So what I'd like to do is build that practice into the video today. So at this point in time, I have these problems for you to try. And if you printed the handout, you already have these. And so you're going to verify algebraically, showing all your steps. You're going to solve and find your solutions between 0 and 2 pi for this one. There's a minus. I gave you an evaluate problem like you did in the previous lesson. But I gave you the breakdown. So when you go to do this, please use 2 pi over 3 minus 9 pi over 4. And then this is a new kind of problem. This says rewrite the expression as sine, cosine, or tangent of an angle. And here's problem A and then a separate problem. And I'm going to give you a hint on this. The hint is this is a one-step problem. So if you are doing more than one step of work, it's too much. All right. And don't stress if you can't get it on your own, because what you're going to do right now is you're going to try all these problems. And then when you're ready, you can continue the video and I'll go through the solutions with you. So if you are not able to get this quickly, don't spend too much time on it, because once you see how I do A, B is going to be a piece of cake for you. Okay, here's my solution for number 3. I expanded because I've trained myself. Anytime I see sine, cosine, or tangent of a sum or a difference, I apply my formula. And then I split apart the fraction, and pretty quickly it got down to tangent alpha plus tangent beta. Here's my solution for number 4. So I expanded. Since this is a minus, I used parentheses here and then distributed the minus. So this should be a minus from the formula. See, that's a plus there. So for cosine, it's a minus in the formula. This minus is between the two original terms. When you expand this one, you get a plus. But because you distribute that negative, you end up with minus. And then, as I mentioned, I like to cancel and combine terms next. Just going to emphasize those SIGNs. Okay, so I like to cancel and combine terms next. And then I like to evaluate. And then I use the commutative property. And then I simplify the equation, and this time I get 2 answers. Just to show you some different ways you might have gone about this. What some people like to do is at this step, they like to move the -2 over and then evaluate. And sometimes I find people get a little stuck here. So I just wanted to show you this. So in order to get sine of x by itself, what you would do is you would multiply both sides by 2 over radical 2, the reciprocal. So either dividing by this, or if you prefer, think of multiplying by the reciprocal. Because what will happen here is all that will reduce, leaving you with sine x. And over here, you're going to end up with 1 over radical 2, just like this work. And then just to show you one other thing that can happen, because as I mentioned, my style is to cancel and combine terms before I evaluate the sine of pi over 4 or whatever angle is there. And just to show you, if you were to evaluate the cosines and sines first before you cancel and reduce, sometimes people get stuck here. And I see why, because to me it looks really a lot more confusing. There are still 4 terms. 1, 2, 3, 4. And 2 of them still cancel. You have a cosine x radical 2 over 2 and a negative cosine x radical 2 over 2. So they do cancel. And then you have 2 of these that are an exact match. Negative sine x radical 2 over 2. So that becomes -2 sine x radical 2 over 2. And then you have the same work that I have. So at that point, you're back to the same place that I was over here. But again, I just personally find this looks much more confusing to me. So that's why I like to cancel and combine before I evaluate something like sine of pi over 4. But totally individual preference. So if you don't mind it the other way, that's fine. For number 5, here's the work I have and the answer. It's okay if you don't show this work, because you might have already written down a 30, 60, 90 or 45, 45, 90 somewhere else. You might be doing a lot of this in your head, or you might be using the unit circle. So this is just for you guys in case you're trying to figure out where I got negative radical 3 and why I have 1 here. That's positive 1. The minus is from the formula. And this one ends up not having a complex fraction, which was kind of different, maybe surprised you. So for this one, there's no complex fraction to clear, so you can jump right into rationalizing the denominator, carefully FOIL, and then watch those SIGNs. You should get 2 plus radical 3 in the end. Okay, number 6. Let's go over part A so that if you had any difficulties, you can then try part B on your own. Here's my answer for part A. So it really is a one-step problem. When I saw cos, sine, sine, that made me think of the cosine u minus v formula, because cos plus sine, sine is the cosine u minus v formula. So what that means is I can take this formula backwards. So I can take this expanded expression and make it cosine of the first angle minus the second angle. And I got cosine 40 degrees. And that was it. So if you had difficulty with A, take another look at B before you continue the video. B was a little more work because I had it in radians. You had to get some common denominators. But it's sine cos and then cosine. That's your sine formula. And when there's a minus, you have a minus for your sine angles, for the angles inside sine. And so if you do 3 pi over 4 minus pi over 6, I got a common denominator of 12 by multiplying by 3 over 3. And then I multiplied this one by 2 over 2 and ended up with sine of 7 pi over 12. And just a quick note for you in your work, just be careful because if you don't have parentheses here in this step, this is actually technically incorrect because you would only be taking the sine of 3 pi over 4 and the negative pi over 6 is just like something that happens afterwards. You want this entire expression to be inside of the sine function, so you do need the parentheses on that one. It's totally okay to put parentheses around the 7 pi over 12 at the end. They're just not necessary because you only have a single angle there. All right, hopefully that went well. The plan for tomorrow is you're going to do some more practice on this, and then I'll actually show you a little something from section 5.5, the next section, but definitely more practice on 5.4 before we continue. Thanks, guys. Have a good day.